Hello, everybody. Today I will be solving problem 4.39 from Griffiths E&M 4th edition. And so this problem states a conducting sphere at potential V0 is half embedded in linear dielectric material of susceptibility chi subscript E, and so which occupies the region Z is less than 0. And so the claim is that the potential everywhere is exactly the same as it would have been in the absence of the dielectric. So we're going to check this claim through some steps. So the first step is in part A. We'll write down the formula for the proposed potential in terms of V0, R, and capital R, which is the radius of our sphere, and little r. And we'll use that to determine the field, polarization, bound charge, and free charge distribution on this sphere. So to begin with, writing down the proposed potential. So for our conducting sphere, our proposed potential is V as a function of R equals V0 times capital R, the radius, divided by lowercase r. And so to find the electric field, we'll use the relationship that the electric field equals the negative gradient of our potential. And so plugging that in, we find that the only component we have for our electric field is in the r hat direction. So the electric field points radially outward, which makes sense. And so here we have that electric field. And so the polarization is given by this equation here. And so all we have to do is plug in our electric field, which we found above. And so here we have that. And so we'll note this polarization is for the part of the sphere embedded within the dielectric, so Z is less than 0. Otherwise, the polarization is 0 for Z greater than 0, also outside the dielectric. Next, we'll find the bound charges. So the surface bound charge first is given by the polarization dotted with the normal vector. And so for our case, we have the polarization, and we'll dot that with a negative r hat because our normal vector points in that direction. And so we'll also note, since it is a surface bound charge, we have it lowercase r at capital R. So that's where we're getting our r over r squared. And so simply doing this dot product, we get this formula for the surface bound charge. And so this is on the surface of the sphere in the dielectric. And the dielectric itself carries no bound charge. And so the reason for that is its normal vector is equal to z hat, which is perpendicular to our to the sphere's r hat pointing radially outward direction. So there is no bound charge on the dielectric itself. And then since there is no free charge in the material, our volume bounded charge is 0. And so those are our bound charges here. And so for the free charge distribution, since V has our potential has spherical symmetry by our configuration, the total charge must be uniform. So writing down the total charge here is equal to the surface charge, the total surface charge times the surface area. So what do we have here? And so we also want to note that V0 is equal to the total charge over 4 pi epsilon naught over the radius. And so alternatively, we can get this in terms of the total charge. And so equating this equation and this equation, we can solve for our total surface charge. So we want to do that here. And so we'll note that these cancel out. And so what we will be left with, and so one of these exponents cancel out with here. So it'll be the potential naught times V naught times epsilon naught over R is our total surface charge. And so with that, we note that the total surface charge is given by the free charge, plus the bounded charge. These are for our surface charges. So the free and bound charge is equal to the total surface charge. And so we can change this equation to find what we're looking for, which is the free charge. And so we note immediately, so this will give us two parts. It's a piecewise function. So for z is greater than 0 when we're out of the dielectric, there is no bound charge. So only the total charge will remain. So that's what we have for z is greater than 0. But for z is less than 0, we're in the dielectric. So using this formula, we know that our total charge is V epsilon naught over R. And we found our bounded charge here above, right here. And so plugging that in, we get minus and then minus epsilon naught, the susceptibility, V naught over R. And so that is equal to, then we can take out our V naught epsilon naught R. And this is addition now. So that's plus, and then our susceptibility. And so that is our formula that we will plug in right here. So it'll be E naught V naught over R times it by 1 plus susceptibility. And so that is our, those are our free charges, free surface charges for our configuration. And so part B says, show that the resulting charge configuration would indeed produce the potential, the V as a function of R. And so we'll do this by first noting that we have the total surface charge is equal to the bound charge plus the free charge, which is epsilon naught V naught over R, which is uniform. And so we can just double check that this is uniform by just noting that for z greater than 0, or in this case, our bounded charge is 0 since we're outside the dielectric, so total is equal to the free charge, which is equal to epsilon naught V naught over R, as we just said. And so, and then inside the dielectric, we have the situation where bound charge is equal to negative epsilon naught susceptibility V naught over R. And then our free charge has to be, we just said, is epsilon naught V naught R 1 plus the susceptibility. And so total would be epsilon naught V naught. And then this is just adding because they have common denominators. We can add them across. And we're pulling out epsilon V naught minus susceptibility plus 1 plus susceptibility over R. And then we'll note this goes to 1. The susceptibilities cancel out. So 0 plus 1 is 1. And so that equals epsilon naught V naught over R. And so they're the same. inside and outside the dielectric, so it is in fact uniform. So the potential of a uniformly charged sphere is given by the fact that here that we have the total charge over 4 pi epsilon naught r. And so we know this total charge is equal to the surface charge for our conductor. The total surface charge times the surface area here. And so canceling these variables out, we got ourselves here, which is this right here. And so we know that the total surface charge we have said is epsilon v naught over r, and so we plug that in here. And so these when these r's, capital R's will cancel out. This epsilon naught cancels out. And so what we're left with is v naught times capital R over r. And this is the potential that we proposed at the very beginning, right here. And so that, so we have shown that the charge configuration would indeed produce this potential that we proposed. So the next part is we're going to appeal to the uniqueness theorem in problem 4.38 to complete this argument. So just to state what problem 4.38 says, it says a volume V contains a specified free charge distribution and the various pieces of linear dielectric material with the susceptibility of each one given. If the potential is specified on the boundaries S of V, so V equals 0 at infinity would be suitable, for example, then the potential throughout the volume is uniquely determined. And so you can look at that to solve that, but we'll just be using this theorem to complete our argument. So we know that our boundary conditions are two. The first one is that as r, the distance away from this sphere goes to infinity, we require that the potential goes to 0. And at r equals the radius of our sphere, the potential must be equal to the to v naught. And so these conditions are these boundary conditions are met because, as we know, for this equation, when we take the limit as r approaches infinity, this will go to 0. And then if we plug in capital R for small r here, all we have is v naught. So our conditions are met, and so everything is consistent. And so since our boundary conditions are met, by the uniqueness theorem, we can say that the potential we found as a function of little r is in fact the solution to our problem. And so the last part is just asking if we could use this same potential for different configurations that they came up with in figure 4.36. And so the first configuration in part A is nearly identical, but the main difference is that our sphere is pushed further into the linear dielectric material. And so for part A, we cannot use the same arguments that we had here because there is no symmetry in how the sphere is embedded. Because before we used to have a symmetry of that exactly half of the sphere was embedded, but now that's no longer true. So we can appeal to our same arguments we used before. So the polarization in the normal vector that we discussed earlier will not be perpendicular, so bound charges will occur on the dielectric surface. So this will mean our potential will be different. So part A cannot use the same potential we solved here. For part B, there is a symmetry in how it's embedded. We know that there is some vertical symmetry right here. And so because of this, since we have a symmetry in how the sphere is embedded, the same potential will work for the configuration in part B. So that is all the parts for this question. And so I hope you enjoyed this solution. Thank you very much.